Good day, everyone. I'm Norman Walberger. Today we're going to be looking at some interesting challenges for programmers to implement the algebra of Boole in a wide variety of situations, especially in the direction of logic gate circuit analysis, but also moving towards propositional logic, which we will be moving towards also. Okay, so we've been talking about the SAT problem, and motivated by that, the idea of having a very big logic expression, maybe from a circuit which has thousands or tens of thousands or maybe even millions of gates. So we have some huge expression and we want to simplify this thing. Or in the SAT case, we want to understand whether this is actually the zero output function or not. So this motivates a very important challenge for us, which is to develop some software tools, some programming tools for Boole reduction in computer algebra systems. So by Boole reduction, I mean the process of taking a big expression, an algebraic expression, which is ultimately a polynomial or a polynumber in our language, in the algebra of Boole. So in other words, with the addition and multiplication purely mod 2. And then to reduce that or convert it to a Boole polynumber. And I remind you that's a very special polynumber or polynomial where the power of any variable appearing is at most 1. Okay, and a computer algebra system, or CAS, is a software environment that allows us to make symbolic manipulations with polynomials. So it's really allowing us to do arithmetic, but not with numbers as so much as with polynomials. This is a very flexible and important development in modern mathematics, the ability to work very efficiently with even very large polynomials. And these days there are many really powerful programs that will allow us to do this, including Axiom, Maple, MuPad, Mathematica, MATLAB, Sage, and others. I happen to use Scientific Workplace to write my papers, like in LaTeX, and that actually has MuPad in it, so it's another kind of environment that draws upon this same kind of underlying mathematical programming languages. So these are the kinds of environments that we're talking about. So if you're interested in one of these, or maybe expert in one of them, we'd like to have software tools in these various environments that allow us to swiftly and efficiently do Boole reduction. Okay, that's the aim. So I want to explain today what that exactly means. All right, so this general challenge is especially important for large integrated circuits or logic gates, but it's also going to be useful for us when we want to rethink, reposition propositional logic, which we will be doing in some videos to come. And it's also connected with AI architecture, artificial intelligence. So underlying a lot of AI are sort of the frameworks for logic, implications, decision making. And I think the algebra of Boole, which is the mathematical environment that I'm trying to promote here, is a really viable alternative for all of these different kinds of directions. So what we want to do is we want to empower our computer system that we're working in to be able to work smoothly in this environment. In particular, that's really crucial, the problem of reducing large expressions to our canonical Boole polynumber form. Okay, so in some sense what we're doing is we're wanting to distance or move away from the classical Boolean algebra point of view on these things, which is now the current framework for these things, and move to this alternate framework, which I'm trying to convince you is actually much more powerful and easier to use and to learn. So with this example, I want to illustrate the various aspects of this challenge. So here is a relatively simple circuit with inputs A, B, and C. It has 2 inverters and 3 AND gates, and the outputs are into this 3-input OR gate. Okay, and the output is called X, and we want to analyze this. So because there are 3 inputs coming into this OR gate, let's introduce some notation. Let's say that H of A, B, and C is A circle sum B circle sum C. In other words, A or B or C. And I remind you that in the algebra of Boole, if we convert that, that's this expression here, A plus B plus C plus AB plus AC plus BC plus ABC. Right? That's how you evaluate three things coming into an OR. So what we have is this function h applied to these three AND gate outputs. The first one here is inverting A and B. So there's a 1 plus A and a B. That's the output of this AND gate. The output of the second AND gate is an A and an inversion of B. So A times 1 plus B. And the third one here has a inversion of B as well as a C. So 1 plus B, C. Okay, so now if we look at this expression here and we input these things here, then we're going to get some big polynomial, and that is the algebra of Boole representation of this circuit. And our problem is to simplify this. Okay, that's our challenge. So if we just do it directly, so if we just think about this as a regular polynomial and we're going to substitute these values in here for little a, b, and c, then we'll get the following. So here's the little a, here's the little b, here's the little c, and then the product of AB is the product of these two, which is right there, and then AC is the product of these ones, which is right here, and then the product BC is the product of those two, which is right here. There's a 1 plus b squared because it's appearing twice. And finally, the ABC is the product of all three of them, which is this one here, and this one here. Okay, so that's just very directly just substituting this into this polynomial. Now, we want to simplify this. We want to do a very particular kind of simplification though. So it's more than just simplifying it using the usual polynomial algebra routines that all these computer algebra systems have. So they all are very capable of very easily simplifying such a polynomial expression. In fact, they'll all get exactly this expression here. So this is what you would get if you just ordinarily evaluate this thing as a polynomial. So individual terms from the linear ones a, b, c up to degree 6 one, a squared b cubed c. And some of them have some coefficients. There's some 3s and 2s and 4s floating around. So what we want to do now is go beyond this. We want to give some more power to our computer algebra system so that it's able to actually further reduce this into a Boole polynumber. This is not a Boole polynumber for two reasons. First of all, we have not evaluated it in the by field. In other words, the 2's have not been set to 0 here. So if we did that, that 4 would become 0. That's 4, there's a 0, there's a 2 here, 2 here. That would be killing those terms, okay? That'd be one kind of reduction that we have to do. And the other kind of reduction is that we have to reduce all the exponents. So a squared is just the same as a. B cubed is the same as b, and so on. So if we did that here, how would we actually do that? The simplest thing would probably be to do the mod 2 reduction first and to eliminate all the, or to simplify all the coefficients mod 2. So this 3 would become an 1, so we just have AB here. This 2BC would disappear, this 4ABC would disappear, so would this one, and so would this one. And then what we would do is we would then reduce all the exponents, basically just rub off all the exponents. Now that's a step that most of these computer systems, in fact I think all of them, do not have any built-in routines that will do that. Right? Currently, with my framework, I have to go and manually rub off all these digits if I want to further simplify this. So what we want is just some little routine that, amongst other things, will very quickly reduce these exponents here to just 1. In other words, basically rub them all off. Okay? But after we've done that, then we need a further application of the mod 2 reduction. Because, for example, this term here, when we lower the exponents, we'll get an AB, but we'll also get an AB from this one. So these two then will cancel if we do a further mod 2 simplification. Okay, so if we do all of that, it turns out that we can get this expression. This is the end result of that simplification that I've just described. The result is A plus B plus C plus AC plus BC plus ABC. It's not quite symmetric because the C is playing a bit of a different role than the A and the B. Now, I want to say that that's well and good. So that's one approach to this, is to use a standard power of a computer algebra system to first obtain a polynomial, and then these Boole reductions that we apply to this final polynomial to reduce it to a Boole polynumber, which is like this one. But actually, if we were going to do this by hand, we could see that we could do the same kind of thing, but in a more efficient way. Okay, and this is going to be important because if we want to write code for this, we want to sort of find relatively efficient ways of doing this, because ultimately we want to deal with very big things, so efficiency is important. So have a look at this stage here. Once we've written down this stage here, we can evaluate or reduce this with the Boole reduction already at this stage before we further simplify it. What do I mean by that? Well, there's a couple of powers here. So there's a 1 plus b squared here. Now that is the same as 1 plus b. So we could rub off this 2 exponent here, and similarly here. Right? So that's a simplification that we can make already at this level before we sort of expand it all out and collect terms. That's obviously going to make that expansion out and collecting terms more efficient. But something else we can notice is that here there's a 1 plus a times a. And 1 plus a times a is always 0, because it's the same as a plus a squared, which is 2a, which is 0. So in fact, this term here, if we recognize that, we could just eliminate that entirely. So by doing that, we would do a sort of a preliminary Boole reduction to a certain extent, and then when we expand things out, then the polynomial that we get at this stage will be simpler, and then a further Boole reduction will go more efficiently. All right, so that's the general kind of thing that we're looking to do. We're trying to think about programming these computer algebra systems so that it's able to smoothly do these kinds of Boole reductions, even on potentially very big algebra Boole expressions. So let's summarize what we've said. First of all, Boole reduction really amounts to applying these two kind of reduction formulas, that x plus x is always 0, and that x squared is x. And in fact, higher powers of x are also equal to x. So the naive approach would be to take a big algebra of Boole expression, which is built up in a polynomial way from variables, the input variables that we have, together with the addition and multiplication of the mod 2 operations. And we do that using just our regular computer algebra system reduction. So just the inbuilt polynomial manipulation software to simplify this. And then what we do is we reduce everything mod 2, cutting down on the coefficients dramatically and removing a lot of the terms. And then we eliminate powers bigger than 1, basically using this rule now, right? So all the powers drop down so that they're just 1. And then finally, we reduce mod 2 again, because that dropping down will have resulted in some more duplications that we can then cancel. And at that stage there, we are in possession of a Boole polynumber, and we can stop. Okay, so that's a very simple kind of procedure that we could try to program. Okay, but we've also talked about a little bit more sophisticated approach, where we perform the Boole reduction at various levels. So not just once at the end, but at various levels as we're kind of expanding or simplifying our potentially big algebra Boole expression. So we perform Boole reduction on subterms, smaller subunits, and then expand those little subunits and then repeat up various levels. So that's a little bit vague. Let me try to illustrate it by this example. So here's an expression in the algebra of Boole, but it's not just a direct polynomial. It's built out of sums and products, but several levels. So it's altogether a product of some sums, but the sums themselves are products, and those products involve sums. So this is a product of sums of products of sums. And we could have a lot of nesting like this. Okay, so what would we do in this kind of situation? We don't want to do the naive thing. The naive thing would be just to feed this into our CAS system and have it spew out a polynomial. Let's just expand this thing out. What we'd rather do is to look at what it is right currently and look at various sort of subterms. So, for example, here there's a product and here there's a product. So in order to simplify this product here, we could look at, say, this little thing here, right? This is a constituent of this bigger product. This is itself a product of three things. We could do Boole reduction on that. First of all, we could remove the 3. Okay, we could expand this out. We could do some mod 2 reduction. We could do reducing the powers. We could do a further mod 2 so that this would then be in a relatively simple form. So then when we could add this to this, hopefully we'll get something relatively simple for that first product. And similarly over here, we would find a reduced expression for this thing, find a reduced expression for this thing, and then add them here at this level. So already this constituent here is going to be a lot simpler than it was ordinarily. Okay. And then we're going to have to multiply these two simplified things still together and then perform the same kinds of operations that I've just described. A mod 2 reduction, a power dropping, and a further mod 2 reduction. Now in addition, we would want to also keep our eye out for some special situations that are going to be useful to identify. In particular, terms like this, a times 1 plus a, appearing. So that's appearing over here, right? You see there's an a times a 1 plus a. If our program can recognize that, then boom, that entire term is going to be 0 and can be immediately dropped out. All right? So that saves us a lot of expansion just by recognizing that kind of factor. The other kind of thing that we can do is to look for powers, things which are powers. Not necessarily powers of individual variables, but powers of expressions. Maybe f of, let's say there's 3 variables, f of a, b, c to some k. K bigger than 1, we can rub off that exponent and just replace it with f of a, b, c. So for example, here there's a 1 plus b plus c all cubed. We could just rub off that 3. Here the 1 plus c squared, we could rub off the 2. Okay. And so when we're doing this, we sort of do it at various stages depending on the nesting of these big expressions. And basically the idea is that we alternate application of our 2 basic rules, that x plus x equals 0 and x squared equals x. So we kind of go back and forth between these to simplify things. All right, so this is a little bit more sophisticated. I'm not saying this is, exactly the best way, but programmers should think about this. Is a very interesting problem. How do we do this efficiently? If you have some big expression with hundreds and thousands of terms, how is your program going to deal with that? Okay, so I think it's a very interesting challenge and a very important challenge in that it really is going to empower us to apply the algebra of Boole in a wide variety of important situations. And I'd like to also make the suggestion that probably we could think about incorporating these Boole reduction functionalities in the actual programming languages. So not necessarily in a computer algebra system, but just some programming language like Python or C or JavaScript or any of these many others. Any programming language that has a kind of a mathematical aspect so that it's able to deal with polynomials and maybe modulo kind of arithmetical operations. Then we could think about having a little subroutine that goes further and does a Boole reduction on a polynomial or a polynomial expression. Okay, so that might be a little bit more general, not just in these computer algebra systems. It might be good to have this kind of functionality as sort of standalone routines that we could add to these programs. Now, if our algebraic expressions are not too big, we can efficiently do Boole reduction on them. But maybe they are very, very big, and doing a full Boole reduction to find the ultimate Boole polynumber for this big expression is too onerous. In that case, or maybe for other reasons, we might be interested in a SAT kind of problem in this algebra of Boole context. So for that, we need to write some code. we need to have some SAT solvers in this algebra of Boole context. So these are sort of going to be comparable to the SAT solvers that have been established. A lot of work has gone in the Boolean algebra story, but they're going to be looking different here. Okay, so what's involved? So let me remind you, let's just look at a special case where we only have 3 inputs for simplicity. That a Boole polynumber, say P of A, B, C, is a polynomial expression which consists of multiples of the following terms. There's a blank here that can either be 0 or 1. A multiple of A, a multiple of B, a multiple of C, a multiple of AB, a multiple of AC, a multiple of BC, and a multiple of ABC. And the multiples are always either 0 or 1. So in effect, what ends up happening is that you get a subset of these things with possibly also a 1. That's what the Boole polynumber looks like. Now, suppose that we're only interested in the question of whether this polynumber is 0 or not. So not what the actual polynumber is, but just whether it's 0 or not. That is the SAT question. Okay? If it's not equal to 0, that means it's satisfiable. So how could we check? Perhaps without actually calculating the whole thing. Okay? So what we need to do is just to find one of these coefficients which is non-zero. And then we can automatically deduce that this polynumber is going to be non-zero. For example, suppose that we figure out that there is an AC term somewhere in here. There's an AC term. Okay, well, that means that this thing is satisfiable because that forces this polynumber to not be the 0 polynumber. So that's a much simpler thing ultimately, especially for big things, than to find the whole thing itself. Okay, and so we might want to have special programs that just address this question. So let me illustrate that with this same example that we had before. So here's the same thing that we had. And let's ask, can we identify whether this thing is 0 or not without necessarily expanding the whole thing and doing a full Boole reduction? Well, I'll just show you how you can decide that in this case. So it gives you a clue for the kinds of things that you might be doing. So what we're looking at is to find one of these terms that has a non-zero coefficient. So if we stare at it, and let's just look at the coefficient of A. Okay, how are we going to get A from this expression? So it's a big product of this thing here and this thing here. So in here, where can we get an A? Well, there's an A appearing right there. There's also an A here, and we can multiply it by 1. That would be an A. But over here, there's no 1. So when we expand this out here, there will not be any term that's just an A. There may be ABs and ACs and ABCs, but there's not going to be any single A appearing here. So in this first bracket, there's only a single A appearing. How about in the second bracket? Well, we've already noted that this term here will be 0, so there's no A contribution coming from that. And what about from here? Well, here's an A. And this A is going to have a coefficient, well, there'll be C's and B's, but the A just by itself will come from the 1 squared times 1. So there will be an A appearing here with coefficient 1. So this first term is A plus something. This second term is A plus something. And then the question is, are there any 1s floating around? No, there are no 1s floating around. There are no 1s floating around either. So it's A plus something with no 1s and another A plus something with no 1s. And then when we multiply those two things, the A times A will be A squared, which is an A. There will not be any A times 1s in either here times a 1 or this A times a 1 over there. That's not going to appear. And so that's the only way we're going to get a contribution to get a power of A. There's no A squareds or A cubes appearing as well. So this thing here, we can see that the coefficient of A, when we expand it out, will be 1. Okay, so that's doing a lot less work than actual expansion and Boole reduction to deduce that this thing is satisfiable. So what we would like is some programs that in the various languages or computer algebra systems that I've discussed that takes a big expression like this, an expression in the algebra of Boole, basically a polynomial kind of expression, and determines whether it's zero or not, along some lines that perhaps like I'm suggesting here. All right, so that's also, I think, an important direction for computer programmers to dig in and to create some nice working tools for us. In our next video, we're going to be looking at a very important correspondence between Boolean functions and Boole polynumbers, which will open up a whole new connection between this subject and an interesting branch of combinatorics. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.